Andrew Yang, a very intelligent and a presidential candidate with a lot of interesting ideas in all kinds of technological fields, tweeted that because of quantum computing, no code is uncrackable. Is he wrong or right?
He was premature, let's say. Wrong. So look, I'm a fan of Andrew Yang. I like I like his ideas. I like his candidacy. I think that he may be ahead of his time with the universal basic income and so forth, and he may also be ahead of his time in that tweet that you referenced. So regarding using quantum computers to break cryptography, so the situation is this.
Yeah.
Okay, so the famous discovery of Peter Shor, 26 years ago, that really started quantum computing, as an autonomous field, was that if you built a full scalable quantum computer, then you could use it to efficiently find the prime factors of huge numbers and calculate discrete logarithms and solve a few other problems that are very, very special in character, right? They're not NP-complete problems. We're pretty sure they're not, okay? But it so happens that most of the public key cryptography that we currently use to protect the internet is based on the belief that these problems are hard.
Yeah.
Okay, what Shor showed is that once you get scalable quantum computers, then that's no longer true. Okay, but now before people panic, there are two important points to understand here. Okay, the first is that quantum supremacy, the milestone that Google just achieved, is very, very far from the kind of scalable quantum computer that would be needed to actually threaten public key cryptography. Okay, so we touched on this earlier, right? But Google's device has 53 physical qubits, right? To threaten cryptography, you're talking, with any of the known error correction methods, you're talking millions of physical qubits.
Because error correction would be required to threaten cryptography.
Yes. It certainly would, right? And how much, how great will the overhead be from the error correction? That we don't know yet. But with the known codes, you're talking millions of physical qubits and of a much higher quality than any that we have now. Okay, so I don't think that is coming soon. Although people who have secrets that need to stay secret for 20 years, are already worried about this. For the good reason that we presume that intelligence agencies are already scooping up data, in the hope that eventually they'll be able to decode it once quantum computers become available. Okay, so this brings me to the second point I wanted to make, which is that there are other public key crypto systems that are known that we don't know how to break even with quantum computers. Okay, and there's a whole field devoted to this now, which is called post-quantum cryptography. Okay, and so there is already so we have some good candidates now. The best known being what are called lattice-based crypto systems. And there is already some push to try to migrate to these crypto systems. So NIST in the US is holding a competition to create standards for post-quantum cryptography, which will be the first step in trying to get every web browser and every router to upgrade, and use some like SSL that would be based on what we think is quantum secure cryptography. But this will be a long process. But it is something that people are already starting to do, and I'm Shor's algorithm was sort of a dramatic discovery. It could be a big deal for whatever intelligence agency first gets a scalable quantum computer, if no one else knows that they have it, right? But eventually, we think that we could migrate the internet to the post-quantum cryptography, and then we'd be more or less back where we started. Okay, so this is sort of not the application of quantum computing, I think, that's really going to change the world.